Hello. Welcome to the ITRI MMSL 2026 online forum. We're excited to bring you the latest breakthroughs in intelligent mechatronics. Our theme this year is Next Generation Intelligent Mobility and Manufacturing, where we'll explore how AI and green energy are reshaping vehicles and the factories of tomorrow. As you can see, our agenda is packed with 6 key innovations. We'll cover everything from electric bus transmission systems, water immersion cooling, to our Edison Award-winning Prognosis monitoring system, and immersive digital twins. Please feel free to use the video chapters below to navigate through the topics that interest you the most. To get us started, let's hear from our leadership. We are honored to have Dr. Bingxiang Yang, Deputy General Director of ITRI MMSL, and Dr. Christine Cho, International Affairs Officer and Representative of ITRI Europe Office, to deliver the opening remarks.
Esteemed participants and distinguished guests, a warm welcome to our 4th online forum. I am Bingxiang Yang, Deputy General Director of Mechanical and Mechatronics Systems Research Laboratories at Industrial Technology Research Institute in Taiwan. We are delighted to have you join us as we embark on an exciting journey into the world of intelligent mechatronics and its transformative impact on manufacturing. In 2026, AI-integrated systems and sustainable automation are no longer just trends. They are reshaping the global supply chain. From autonomous factories to next-generation mobility, these innovations are driving net-zero operations and building unprecedented industrial resilience. Throughout this forum, we will showcase how our R&D solves real-world challenges. You will see how AI-driven manufacturing and mobility technologies are accelerating the future of our industry. Our team is excited to share their insights with you, and we want to hear from you as well. Please engage with us by leaving a comment below or filling out the inquiry form in the description box. Your feedback is invaluable, and we believe that diverse perspectives will lead to innovative solutions and a deeper understanding of the potential unleashed by intelligent mechatronics.
Thank you, Bingxiang, for this opportunity. Hi, everyone. My name is Christine Zhou, the International Affairs Officer and the representative of ITRI in Europe. It's a great pleasure to be here with you all today. 2026 marks a significant milestone for ITRI. Not only are we celebrating our 10th recognition at the R&D 100 Awards, we are also continuing to lead global R&D discussions as the chair of the ITRI network. Behind this success are more than 6,000 outstanding researchers. Our mission is to advance industrial development, create economic value, and improve societal well-being through technological innovation. We work to deliver new value and uncover future needs for our partners, while proactively addressing global trends, from urbanization and population aging to the evolving demands of climate change. With these goals in mind, today's session brings together experts from ITRI Mechanical Lab to share our latest breakthroughs in next-generation electric mobility, AI-driven platforms, and green manufacturing solutions. These technologies are driving global industrial transformation and digitalization, and they open significant opportunities for cooperation between Taiwan and Europe. I look forward to the insights and connections that will emerge from today's session, and I warmly invite you to reach out to our Europe office to explore future partnership.
Thank you, Dr. Yang and Dr. Cho, for the warm welcome. To help you better understand our core capabilities and how we drive industrial transformation, we'll start with a brief overview of ITRI MMSL, also presented by Dr. Bingxiang Yang. Let's take a look.
So in this presentation, I am going to give you a quick overview on the capabilities of enabling future smart manufacturing and vehicle technologies. MMSL consists of nearly 700 employees, with the majority of whom are researchers with master or doctor degrees. With over 1,300 active patents, our aim is to provide technologies that enhance intelligence, precision, and sustainability for the industry. We focus on 2 major areas: The first one is intelligent manufacturing, covering robotics, smart factories, semiconductor equipment, and green technologies. The other one is intelligent mobility, where we develop UAVs, railway systems, electric vehicles, and autonomous driving. In intelligent factories, we connect equipment and materials through the Internet of Things. By integrating sensors with our proprietary algorithms, we quantify equipment status in real time. This allows us to optimize parameters through AI at every stage, ensuring superior quality control and a much smarter manufacturing process. Next, let's take a look at 3 core technologies making manufacturing smarter. First, our AI water jet system. It uses AI to optimize water jets for waste tire recycling with 100% accuracy. This circular economy breakthrough just won the 2025 R&D 100 award, proving its global impact. Next is our vibration suppression technology. By using customizable dampers, we can eliminate vibrations in machine tools and aerospace equipment, as you can see from the dramatic reduction in the vibration charts here. Third, we use digital twins and XR to create immersive interactions. This digitalizes SOPs for complex tasks, which can be a game changer for precision industries like semiconductors and aerospace. Beyond systems, we develop critical subsystems to strengthen the domestic supply chain. On the left, we provide high-precision hardware like BC rotary spindle heads and hydrostatic rotary tables, achieving zero frictional loss and sub-0.1 mm error rates. The brain of these machines is our advanced multi-axis controller. It features an open architecture and fully digital EtherCAT communication, supporting simultaneous 5-axis machining. This vertical integration is already being used to manufacture parts for high-end applications, including indigenous aircraft and mask embossing rollers. Another strategic focus is hydrogen energy. We are building a complete value chain, from production to power generation. On the production side, we develop high-efficiency AEM electrolyzers, focusing on key electrode materials and thermal management. For power generation, we specialize in fuel cell systems. This includes lightweight, air-cooled stacks that give UAVs long-endurance capabilities, as well as high-power, liquid-cooled systems for heavy-duty electric trucks. By integrating materials, modules, and control systems, we are providing the essential technologies for a zero-emission future. As many of you know, Taiwan is a global leader in semiconductor manufacturing, and MMSL plays a vital role. We utilize multi-physics simulation for processes like plasma etching and advanced packaging. Beyond that, we provide specialized grinding and polishing equipment for diverse materials. We work closely with industrial partners to develop key modules and equipment for semiconductor manufacturing. We are also committed to green manufacturing, integrating low fluoride and low carbon solutions across the industry. To integrate these complex processes, advanced robotics are essential. Over the past 25 years, we have built a roadmap spanning from service and industrial robots to AGVs and AMRs. Recently, we have shifted our focus toward human-related robotics. This includes our R&D 100 winning exoskeleton robots and advanced human-like robotic hands designed to enhance human capabilities and support critical applications, such as the surgical and medical fields. For mobility, we offer full-stack EV solutions, from fast charging stations and battery packs to vehicle control units and motors. We don't just build parts, we work with industrial partners to develop entire systems. Notably, we were the first team in Taiwan to receive an autonomous driving license for open roads. Today, our fleet includes a wide range of autonomous vehicles adapted for various scenarios. Our impact is global. For instance, we've deployed high-definition mapping in Japan, and in Australia, we successfully demonstrated 35-ton autonomous trucks operating on high-speed motorways. Moving from ground to air, we specialize in high-payload UAVs for industrial applications. By combining our flight control expertise with high-power motor technologies, we provide integrated systems tailored for complex missions. To conclude, our work is driven by vision, passion, and action. We are committed to being your trusted partner in turning innovative ideas into reality. With this, I give you a quick overview of our capabilities. If you are interested in any of the technology, feel free to contact us. Thank you.
Thank you, Dr. Yang, for that comprehensive introduction. It's clear that ITRI MMSL is at the forefront of combining intelligent technology with practical industrial applications. Now, with that big picture perspective in mind, let's move into our tech insights to see these innovations in action. If anything sparks a question during the video, please share your thoughts in the comments. We'd love to engage with you. First, let's explore the innovative sphere of electric vehicles. Let's welcome Ming-Xin Yang to share the latest on transmission technology for electric buses.
Good day, everyone. I am Ming-Xin Yang. It is a pleasure to be here at this online forum to share our technical achievements regarding transmission technology for electric buses. As the policy for full electrification of passenger buses by 2030 progresses, the electrification of transportation has become an inevitable trend. In the development of electric buses, the performance of the transmission system directly affects the vehicle's efficiency and terrain adaptability. Today, I will introduce our precision transmission solutions, covering the entire process from duty cycle collection and modeling to final testing and verification. Passenger buses play a vital role in public transportation. When the power source shifts from internal combustion engines to electric motors, the transmission module must be adjusted accordingly to maintain vehicle performance. Although motors offer a wider operating range, driving a bus solely with a motor can be challenging on steep or mountainous terrain. As the incline increases, the required driving force at the wheel end rises sharply. Relying solely on larger motors is often impractical due to constraints in vehicle space and battery system capacity. Therefore, designing a dedicated gearbox for electric buses is a necessary option to enhance climbing capability while optimizing chassis space. Our transmission module is characterized by high efficiency and high reliability. We utilize a coaxial two-stage planetary gear configuration, which effectively reduces both axial and radial dimensions, addressing the challenge of limited installation space in bus chassis. Regarding life cycle management, we aim for consistency between component life and the vehicle's actual service requirements to avoid cost waste caused by over-engineering. Furthermore, through precision gear profile modification, we have successfully compensated for the elastic deformation of the system under load. This ensures that the tooth contact stress remains centered, increasing transmission efficiency to a peak of 97.7%, and significantly reducing operational noise for a more comfortable ride. The first step in our design process is establishing accurate environmental parameters. We conducted on-site data collection on the rugged and steep bus routes in the Matsu region. By measuring road data and integrating the target vehicle's parameters, we converted the road conditions into a load cycle representing the torque and speed distribution of the gearbox. This statistical data provides a precise map of the stress levels during actual operation. Through data compression techniques, we calculated the fatigue life of the gearbox to ensure it meets a service mileage requirement of over 200,000 km. This data-driven approach ensures the product's durability under extreme terrain challenges. During the modeling stage, we designed a single-speed gearbox tailored for the Matsu duty cycle, compatible with a 220 kW motor. We utilized KISS software to optimize gear parameters, including the number of teeth, module, pressure angle, and addendum modification coefficients, finding the optimal balance between efficiency and contact ratio. To address the challenges of inclined roads, we designed a specialized top hat, housing, and internal lubrication structure. We added lubrication ports to the housing faces and gear shafts, along with baffles around the gears to guide oil flow. This design ensures that even when the vehicle is frequently tilted on slopes, the lubricant is effectively directed to critical components, maintaining excellent lubrication and preventing overheating. Components within a transmission system are finite stiffness objects that undergo microdeformations under load. These deformations can cause the ideal gear contact to become misaligned, negatively impacting service life. We used Romax system analysis software to evaluate these deformations and implemented precision gear profile modification accordingly. Gear modification involves micron-level adjustments to the tooth profile and led to offset the bias caused by elastic deformation. After modification, the maximum contact stress successfully shifts from the edges back to the center of the tooth face. This optimization is a core technology for enhancing transmission efficiency and reducing system vibration. The final stage is the physical verification. We utilized the Super Flow Transmission Test Bench to conduct trial runs, high-speed tests, and efficiency measurements. Regarding noise, vibration, and harshness, the spectrum analysis from 0 to 3000 revolutions per minute showed stable vibration sources with no abnormal resonance. Gear tooth contact patterns also confirmed the effectiveness of our modifications. For structural strength, we performed verification on a static torque test bench. The results confirmed that the module can stably output a maximum torque of 2,800 Nm, with structural stiffness meeting all design specifications. In conclusion, this gearbox successfully achieved a peak efficiency of 97.7%, providing a robust and efficient power transmission solution for electric buses operating in complex environments. Thank you.
Thanks, Mingxin, for that insightful look into electric bus systems. Next, we're staying with mobility but shifting focus to high-efficiency power. Let's invite Jun Kai Chiu to talk about the 800 volts high-power density SiC inverter.
Hello everyone, I'm Jun Kai Chiu. Today, I'll be walking you through ITRI's advancements in high-efficiency SiC inverter technology, specifically how we're optimizing power density and performance for the next generation of electric mobility. This slide explains the role of the inverter in electric vehicle powertrain systems and highlights the key breakthroughs enabled by SiC technology. First, in an EV system, the battery provides DC power, while the traction motor operates on AC power. Therefore, an inverter is required to convert DC into AC to drive the vehicle. In other words, the inverter is a core energy conversion unit in the EV powertrain, and its efficiency directly impacts overall vehicle energy consumption and driving range. However, conventional silicon-based power devices face several limitations under high voltage and high power conditions. These include higher switching losses, reduced conversion efficiency, and increased thermal management challenges, which require more complex cooling designs. In addition, the overall system size tends to be larger, making it difficult to achieve high power density. These challenges become even more significant in commercial vehicles and high power applications. To address these issues, this work focuses on adopting silicon carbide power devices based on an 800 volts high voltage platform. SiC devices offer lower switching losses and higher voltage capability, which significantly improve efficiency while reducing thermal losses. Building on this, we further integrate hardware and software design, including control strategies and thermal management, to enable a high power density inverter system. On the right-hand side, you can see a comparison between Si and SiC technologies. SiC demonstrates clear advantages in terms of losses, efficiency, and system size. In the bottom right corner, you can see the inverter module developed by ITRI. Through system integration and design optimization, we achieve both high efficiency and compact design. Overall, this technology not only enhances EV performance, but also lays a critical foundation for future high-power, high-efficiency electric mobility solutions. This slide presents the three key advantages of our 800 volts SiC inverter system, namely high power density, compact design, and an AUTOSAR-based software architecture. First, in terms of high power density, the system is built on an 800 volts high voltage platform, which significantly enhances energy conversion efficiency and output capability. The maximum system efficiency exceeds 99%, with a peak output power of over 400 kilowatts. In addition, the power density reaches more than 100 kilowatts per liter. This means higher power output can be achieved within the same volume, providing a critical advantage for electric vehicle applications where space is limited and high power performance is required. Second, for compact design, we optimize both system integration and thermal management. In particular, we adopt ceramic capacitor modules. Compared to conventional capacitors, they offer higher voltage tolerance and superior high-frequency characteristics, allowing a significant reduction in component size under the same electrical performance requirements, and further improving overall power density. In addition, a shared liquid cooling channel is designed for both the power module and capacitors, which enhances heat dissipation efficiency while reducing system complexity. Through these integrated design approaches, the total inverter volume is reduced to approximately 3.5 liters, achieving a highly compact and high-density design. Finally, from the perspective of software and control architecture, the system adopts an AUTOSAR-based framework to enhance modularity, scalability, and industry compatibility. It is also built on a multi-core high-performance computing platform, enabling advanced motor control strategies to further improve voltage utilization and overall system efficiency. In summary, through the deep integration of power electronics, thermal management, and software architecture, this system achieves high performance, compact size, and high flexibility, making it a key enabling technology for next-generation electric vehicles. This slide presents the three key advantages of our 800 volts SiC inverter system, namely high power density, compact design, and an AUTOSAR-based software architecture. First, in terms of high power density, the system is built on an 800 volts high voltage platform, which significantly enhances energy conversion efficiency and output capability. The maximum system efficiency exceeds 99%, with a peak output power of over 400 kilowatts. In addition, the power density reaches more than 100 kilowatts per liter. This means higher power output can be achieved within the same volume, providing a critical advantage for electric vehicle applications where space is limited and high power performance is required. Second, for compact design, we optimize both system integration and thermal management. In particular, we adopt ceramic capacitor modules. Compared to conventional capacitors, they offer higher voltage tolerance and superior high-frequency characteristics, allowing a significant reduction in component size under the same electrical performance requirements, and further improving overall power density. In addition, a shared liquid cooling channel is designed for both the power module and capacitors, which enhances heat dissipation efficiency while reducing system complexity. Through these integrated design approaches, the total inverter volume is reduced to approximately 3.5 liters, achieving a highly compact and high-density design. Finally, from the perspective of software and control architecture, the system adopts an AUTOSAR-based framework to enhance modularity, scalability, and industry compatibility. It is also built on a multi-core high-performance computing platform, enabling advanced motor control strategies to further improve voltage utilization and overall system efficiency. In summary, through the deep integration of power electronics, thermal management, and software architecture, this system achieves high performance, compact size, and high flexibility, making it a key enabling technology for next-generation electric vehicles. This slide presents the practical deployment results of our technology, highlighting successful applications across different vehicle segments. Our technology has been transferred to multiple domestic system integrators and successfully deployed in a variety of vehicle platforms, including electric buses, commercial vehicles, and passenger vehicles. In the electric bus segment, the technology has been transferred to Takeo and Tatung, and applied to platforms such as our AC and Tron. These buses are already operating in public transportation systems, demonstrating strong reliability and stability in real-world conditions. In the commercial EV segment, the technology has also been successfully implemented. Systems developed by Tayco have been deployed in China Motors CPEV platform, while Shilin Electric has applied the technology to the ET35 electric light-duty truck. These vehicles are already in operation, validating performance under high-load and long-duration usage scenarios. For passenger vehicle applications, the technology has further expanded into the international market. Through collaboration with ACBEL, the powertrain system has been adopted in a Japanese OEM passenger vehicle program, demonstrating its global competitiveness and application potential. Overall, this project goes beyond technology development. Through effective technology transfer and strong industry collaboration, the solutions have been successfully commercialized and deployed across multiple vehicle segments, from electric buses to commercial and passenger vehicles, demonstrating a high level of technological maturity and industrial readiness. Thank you for joining me today, and I look forward to your feedback.
Thank you, Jun Kai. Now, let's move from vehicles to the world of robotics. We have Ching-Han Tsai here to introduce RoboTWIN General Artificial Intelligence Training Platform.
Hello everyone, I am Ching-Han Tsai from ITRI MMSL. Today, I will introduce a robotic platform that integrates general-purpose AI with high-fidelity simulation called RoboTWIN. I will explain how physics AI combines perception and control to strengthen sim-to-real integration, and how these technologies have been deployed in production lines in Taiwan, followed by case studies and application results. RoboTWIN is a robotic platform with high-fidelity physics simulation capabilities, built around 3 core functions and 4 major modules. One of its key strengths is the ability to rapidly virtualize real production lines. Even in a CAD-free environment, it can complete production line and equipment modeling, enabling AI training, validation, and testing in simulation. The platform then connects the virtual and physical worlds to deploy the results to real production lines and robot control systems. RoboTWIN consists of 4 major modules that can interface with different AI agents, supporting multimodal interaction and recognition such as text and image understanding. Through perception and environmental awareness, the platform enables robots to understand their surroundings and make decisions. It further incorporates real-time path generation to produce execution strategies aligned with manufacturing process requirements. During sim-to-real integration, operational data is continuously fed back into the system for ongoing optimization and refinement. In AI training, sufficient data and strong generalization capability are essential. RoboTWIN uses generative approaches to build diverse training environments, covering various terrains, such as flat ground, rough surfaces, and stairs, as well as different surface conditions, including sand and wet areas. This makes the training scenarios richer and more representative. It can also simulate a wide range of factory variations, including changes in workpiece shape, size, lighting conditions, and different types of obstacles to support robot learning. The platform supports multiple robot forms, including humanoid, bipedal, quadrupedal, wheeled, and robotic arm systems, enabling cross-platform and cross-modality integration. For systems with multiple degrees of freedom and heterogeneous sensor integration, RoboTWIN further applies sim-to-real calibration algorithms to reduce the gap between simulation and reality. This improves simulation fidelity and enables smooth sim-to-real connection and deployment. The RoboTWIN platform has been successfully deployed across multiple industries in Taiwan, including the steel, powder metallurgy, and hand tool sectors within the metal processing industry. It enables synchronized multi-axis control and sim-to-real integration in real production environments. Representative applications include a large-scale gantry welding robot system for the steel industry, a high-speed robotic pick and inspection system for powder metallurgy, and automated assembly solutions for the hand tool industry. Taking the gantry welding robot as an example, RoboTWIN enables effective sim-to-reel integration, achieving a 95% first-pass yield in real machining and welding paths, with positioning and processing accuracy of less than millimeters. In addition, the platform continuously collects welding process data to support AI training and the establishment of an AI-powered welding process database. Taiwan's metal processing industry generates over 1 trillion NT dollars in annual output and plays a critical role in national manufacturing competitiveness. However, the sector still faces three major pain points: the lack of 3D CAD models, irreversible manufacturing processes such as welding, cutting, and grinding, and the complexity of handling large-scale workpieces. With ITRI's high-fidelity simulation and AI-driven robotic simulation and control technologies, manufacturers can build virtual production environments for pre-deployment validation and optimization, reducing cost and risk while improving automation efficiency and process reliability. Thank you for your time, and I welcome your feedback.
Thanks, Shenghan. Moving forward, let's look at how green manufacturing is evolving. Let's welcome Ya-Chi Ho to talk about a cool solution. Literally, the water immersion cooling system for high-power computing chips.
Hello everyone, I am Ya-Chi Ho. I am a manager at the Industrial Technology Research Institute, also known as ITRI in Taiwan. I work in the Green Manufacture Technology Division, focusing on thermal management and cooling technologies for high-power electronic systems. In recent years, we have focused on developing water-based immersion cooling systems for AI and high-performance computing applications. These systems aim to solve the challenges of high heat generation and improve system efficiency. Today, I am very happy to share our work with you. I hope our technology can provide a simple, green, and effective solution for future computing systems. This slide shows our water-based immersion cooling technology. In this system, electronic components are directly placed in water. This allows heat to be removed quickly and efficiently. Compared to traditional air cooling, water can carry much more heat, so the cooling performance is much better. Our system is designed for high-power chips, especially for AI and high-performance computing. A single chip can generate up to 2,000 watts of heat, and the heat density can be higher than 300 kilowatts per cubic meter. This level of heat is very difficult to handle with conventional cooling methods. One key advantage of our system is the use of water as the cooling fluid. Water has a very high heat capacity, which means it can absorb a large amount of heat and keep the system stable. It also helps reduce temperature fluctuations and improve system reliability. In addition, our design removes the need for complex piping systems. This helps reduce system cost and makes the system simpler to build and maintain. We also combine the system with a heat exchanger and natural cooling sources, which can greatly reduce energy consumption. Another important advantage is that water is environmentally friendly. It has zero global warming potential, and it is easy to recycle. This makes our solution green and sustainable. Overall, our water-based immersion cooling system provides a safe, efficient, and scalable solution for future AI and HPC systems. Here shows why we choose water as the cooling fluid. We compare water with chemical fluids in several important areas. First, water has much better cooling performance. It can handle very high heat, including chips over 2,000 watts. Chemical fluids, on the other hand, are limited when the heat is too high. This makes water a better choice for future AI and high-power systems. Second, water is much cheaper. It is easy to get and does not require special materials. Chemical fluids are expensive and increase the overall system cost. This is very important for large-scale data centers. Third, water is better for the environment. It has zero global warming potential, which means it does not harm the environment. Chemical fluids usually have high global warming potential and can cause environmental problems. In terms of safety, water is non-toxic and safe to use. Chemical fluids may have health risks and require careful handling. Water is also easy to recycle, while chemical fluids are difficult to recycle and dispose of. Finally, water-based systems are simpler. They do not need complex piping or sealed systems, so maintenance is easier. Overall, water is a more efficient, safe, and sustainable solution for immersion cooling. This slide shows how we move from design to real system and final validation. It proves that our technology is not only an idea, but a working solution. First, we have strong design capability. We created a complete system design, including the structure, piping, and cooling layout. This allows us to build a full system, not just a small test setup. Next, we built a real prototype system. As you can see in the picture, the system includes multiple immersion tanks and control units. This shows that our technology can be integrated into a practical and scalable solution. We also designed the system to be manufacturable. This means the system can be produced in real applications, such as data centers or AI server environments. Most importantly, we have completed long-term validation. We tested the system for over 180 days to ensure stability and safety. The results show no leakage and stable operation over time. Finally, we verified the cooling performance. Our system can handle more than 2,000 watts of heat. The temperature remains stable, which proves that the system can support high-power chips. In summary, we have completed design, built the system, and successfully validated its performance. This makes our solution ready for real-world applications. What makes Taiwan an ideal hub for developing water cooling technology? First, Taiwan is an island, so it is surrounded by a large amount of seawater. This means we have easy access to a stable and continuous cooling source. In addition, Taiwan has a subtropical climate, which brings a high amount of rainfall every year. Taiwan also experiences frequent typhoons and seasonal monsoons. These weather conditions bring a large amount of fresh water. As a result, Taiwan has many rivers, reservoirs, and groundwater resources. Another important factor is Taiwan's geography. The island has many mountains, which help collect and store water. This water is then directed into reservoirs and rivers, making water resources more stable and reliable. Taiwan also has well-developed water infrastructure. This includes dams, reservoirs, and water management systems. These systems make it easier to use water efficiently for industrial applications. Because of these advantages, Taiwan has access to both fresh water and seawater. This makes it very suitable for water-based immersion cooling systems. Taiwan has natural and infrastructure advantages that support the development of efficient, sustainable, and large-scale cooling solutions. In summary, our water-based immersion cooling system provides a simple and powerful solution for next-generation AI chips. We have demonstrated strong design capability, built a real working system, and successfully validated its performance, including over 2,000 watts heat removal and 180-day long-term testing. Compared to traditional and chemical cooling methods, water offers better performance, lower cost, and zero environmental impact. In addition, Taiwan's abundant water resources make this solution highly practical and scalable. We believe this technology is ready for real-world applications and global collaboration. Thank you.
Thank you, Yachi. Next, we're diving into the future of factory efficiency. We're proud to share that the next solution has recently earned a gold medal at the Edison Awards. Let's invite Junjia Wang to tell us more about the Prognosis monitoring system.
Hello, I'm Chunqi Wang, Division Director of the Smart Factory System Integration Technology Division at ITRI. Today, I'm pleased to introduce our Prognosis Monitoring System, PMS. The Prognosis Monitoring System, or PMS, is an AI-powered predictive maintenance platform designed for rotating machinery such as motors, pumps, and gearboxes. What makes PMS unique is its hybrid intelligence architecture. It combines physics-based models, expert diagnostic knowledge, and artificial intelligence algorithms to continuously monitor equipment health in real time. First, PMS provides real-time monitoring, allowing operators to detect abnormal conditions before failures happen. Second, its AI predictive analytics engine can estimate remaining useful life, helping manufacturers schedule maintenance more accurately and avoid unnecessary downtime. In addition, PMS includes automated fault diagnosis for common issues such as bearing damage and gear wear, significantly reducing manual inspection effort and maintenance labor. Another major advantage is deployment flexibility. PMS can be used through Windows applications, web-based dashboards, portable diagnostic devices, MEMS sensor-based edge systems, and software libraries for seamless integration into existing industrial platforms. With these capabilities, PMS transforms traditional time-based maintenance into intelligent predictive maintenance, helping industries improve reliability, reduce operating costs, and achieve smarter asset management. What makes PMS stand out lies in these three core capabilities. First, PMS provides real-time health monitoring. It continuously monitors machine conditions to detect abnormalities before failures occur. By combining ISO-based health indicators with customizable AI models, the system can adapt to different types of equipment and operating environments while enabling early warning and reducing unexpected downtime. Second, PMS delivers predictive RUL analytics. It predicts both equipment health and remaining useful life, allowing companies to make smarter maintenance decisions. In real-world applications, the system typically achieves less than 15% prediction error, helping optimize maintenance scheduling and extend equipment lifespan. Third, PMS features intelligent fault diagnosis. It can automatically detect common faults such as bearing damage and gear wear. Supporting multiple fault types with over 90% accuracy, the system significantly reduces manual inspection effort and maintenance time. Together, these capabilities transform traditional maintenance into a predictive and data-driven approach, improving reliability while lowering operational costs. PMS is designed for a wide range of industrial applications, especially in high-value and mission-critical sectors. Today, it has already been deployed across multiple industries, including electronics and semiconductor manufacturing, general rotating machinery, machine tools, petrochemical plants, wind energy, and railway transportation systems. These industries share a common challenge. Equipment reliability is directly linked to operational performance and business profitability. In such environments, even a single unexpected failure can lead to significant financial loss or system disruption. What makes PMS particularly valuable is its ability to adapt across these diverse sectors. Whether it is high-precision semiconductor equipment, large-scale energy systems, or continuous manufacturing lines, PMS provides consistent and reliable predictive maintenance capabilities. This broad applicability allows PMS to scale efficiently across industries, positioning it in a large and rapidly growing predictive maintenance market. What truly demonstrates the value of PMS is its proven impact in real industrial environments. Today, PMS has been deployed across 6 major industries, with over 200 enterprise pilots and more than 1,500 machines in operation. It is already trusted by leading global manufacturers, including UMC, Micron, and ASE. More importantly, the impact is measurable. We have improved diagnostic accuracy from 70% to over 90%, while reducing analysis time from 10 minutes to just 1 second. In semiconductor applications, PMS helps prevent unexpected downtime and can save up to $5 million per incident. In wind turbine systems, it has increased equipment uptime from 70% to 92%, significantly improving operational performance. In the following video, you can see a real-world deployment example demonstrating how PMS performs real-time monitoring and remaining useful life prediction in actual industrial environments.
In the era of smart manufacturing, predictive maintenance for industrial equipment has become the key to staying competitive. Across global production lines, rotating machinery consume about 70% of all power, serving as the prominent driving force of manufacturing. Any unexpected failure can lead to tremendous losses. ITRI has pioneered the Prognosis monitoring system, blending 3 decades of vibration monitoring expertise with advanced AI algorithms. Through multiple upgrades and flexible design, it visualizes machine health at a glance. The system offers 3 key strengths. First, it combines vast historical data, domain expertise, and AI models to achieve over 90% in failure prediction and keep false alarms below 5%. Second, it is fully automated with no manual intervention required, supporting remote deployment and synchronized monitoring across multiple machines. Third, its modular design allows quick adaptation across different industries. With cross-platform integration, PMS aligns with global smart manufacturing trends, paving the way for sustainable and resilient growth. So far, this technology has been adopted across 6 major sectors: semiconductors, machinery, petrochemicals, energy, rail transport, and smart manufacturing. Over 1,500 systems have been deployed, serving more than 200 companies. In the energy sector, equipment availability improved from 70% to 92%. In the semiconductor industry, a single case saved up to $5 million. The technology has also been transferred to sensor manufacturers, bringing in over 2,000 orders from leading chip makers and foundries. Furthermore, PMS is also expanding into the US and European markets as a flagship of Taiwan's smart manufacturing innovation. The Prognosis monitoring system. Predict early, maintain smart, perform stronger.
To sum up, these results clearly show that PMS is not just a technology, it's a proven innovation driving the future of predictive maintenance. With that, thank you for your attention today. I look forward to your questions and feedback.
Thanks, Junjia. To wrap up our tech sessions for this track, we're looking at the intersection of AI and immersive technology. Let's welcome Shuapeng Liang to talk about digital content generation for immersive interaction with digital twins.
Hello, everyone. I am Shuapeng Liang, Senior Researcher at ITRI MMSL. It is a pleasure to be here with you today to share our latest developments in digital twin technology. This presentation introduces a 4-year research program developed at ITRI's Mechanical and Mechatronics Systems Research Labs. The technology, titled Digital Content Generation for Immersive Interaction with Digital Twins, addresses a critical gap in modern smart manufacturing. When a CNC machine fails at a remote factory, traditional video calls cannot convey the depth of real-time machining state, spindle load, axis coordinates, or cutting dynamics. needed for expert diagnosis. Our team started in 2023 by building a multi-user VR/AR platform that synchronizes live controller data with a 3D kinematic model, enabling field operators and remote experts to diagnose faults together in a shared virtual space. Over 4 years, we evolved from basic data projection to unsupervised AI anomaly detection, then to multi-agent SOP generation, and finally to full OpenUSD-based cross-platform integration. The result is a unified system that compresses a 13-hour fault resolution cycle down to 3 hours, trains AI quality models with just 50 samples, generates standardized SOP documents in 2 hours instead of 20, and enables heterogeneous equipment, CNC, AMR, and warehouse robots, to be virtually commissioned from a single platform. This presentation walks through the core technology, competitive advantages, real industry deployments, and a detailed success story from Linkia Technology. Here, we outline the 4 core technology modules that form the backbone of our system. Immersive Collaborative Diagnostics establishes a real-time VR/AR workspace where multiple roles, floor operators, remote engineers, and supervisors can interact simultaneously. The platform pulls raw data directly from the CNC controller's native API rather than relying on secondary sensors, eliminating latency and ensuring data fidelity. The virtual scene auto-renders the machine's kinematic chain, tool tip trajectory, and 4 synchronized data dashboards, enabling the remote expert to observe submillimeter vibration behavior as if standing next to the machine. AI milling quality assessment replaces static threshold alarms with a self-adaptive dynamic control band trained on unsupervised learning. A baseline of only 50 good sample cutting runs is sufficient, reducing typical AI onboarding data requirements by 80%. The model continuously recalibrates its upper and lower energy bounds as the machining stage changes, preventing false positives while detecting genuine anomalies with 100% accuracy in validated test scenarios. Multi-agent SOP generation deploys 2 cooperating LLM agents, a Llama 3.2-11B model that generates the full SOP task definition, and a 3B model that scores and iterates each step. A 20-step procedure that previously required a senior engineer to spend 20 hours now takes under 2 hours, with an 80% full text accuracy rate and a 90% step-level accuracy rate. OpenUSD cross-platform integration brings together CNC, AMR, and warehouse systems in a shared NVIDIA standard digital space, enabling virtual commissioning and industrial metaverse deployment. Next, let's look at the 3 competitive differentiators that set our technology apart from international benchmarks from robot and machine tool companies. The first advantage, Immersive Collaborative Diagnostics, directly addresses the overseas service cost problem. When a production line halts, the downtime cost alone can reach $2,500 per hour. Sending a senior engineer overseas adds a further 5 man-days of travel cost per incident. Our platform enables the same expert to join a fully contextualized virtual diagnostic session within minutes. In validated deployments, fault resolution dropped from 13 hours to 3 hours, a 76% reduction, without any physical travel. The second advantage, AI milling quality assessment, solves the knowledge transfer crisis facing the precision machining industry. Experienced machinists who can identify overcut causes by sound or feel are retiring faster than they can be replaced. Our AI model encodes that diagnostic logic numerically, classifies faults as either program side or mechanical side errors, and does so with no additional sensor hardware, lowering the total cost of AI adoption significantly. The third advantage, adaptive scene generation, targets the flexibility challenge of high-mix, low-volume manufacturing. As factories reconfigure their lines more frequently, the cost of reprogramming AGV paths, revalidating safety fences, and retesting robot handoffs accumulates. Our scene generation engine accepts a natural language description of the new line layout and automatically composes the virtual commissioning environment, targeting a 50% reduction in setup time and a greater than 95% scene acceptance rate. This slide summarizes 3 industrial use cases. In 2023, we partnered with system integrator and machine tool builder to establish a digital manufacturing showcase at an university training site. The deployment provided the first real-world validation that our immersive interface is intuitive enough for both teaching and production use. The key outcome: fault resolution time fell from 13 hours to 3 hours, confirming that remote expert access through our VR platform is a viable substitute for on-site presence. In 2024, we scaled into 2 high-value sectors. At semiconductor sputtering equipment manufacturer site, we digitized 18 standard operating procedure apps spanning manufacturing, after-service, and quality assurance. The AR-guided assembly workflow, combined with real-time AI learning assessment, compressed staff training cycles from 90 days to 30 days. In 2025, we entered international territory by facilitating a collaboration between internation companies. We built a virtual casting production line that overcomes the time zone and geographic barriers of cross-border commissioning. The expected result: large workpiece setup and alignment time reduced by 33%, 120 minutes to 80 minutes, and anomaly diagnosis time cut from 3 hours to 1 hour. Here is the case that deserves deeper examination, as it represents the full end-to-end deployment of our platform in a high-precision semiconductor context. We collaborate with a company that manufactures sputtering equipment used in semiconductor thin-film deposition. The assembly process involves complex multi-unit procedures across 3 departments: manufacturing, after-sales service, and quality assurance, each with distinct SOP requirements. Prior to our intervention, staff turnover exceeded 30% annually, training new technicians took 90 days, and overseas service calls required 5 man-days per case at a personnel cost of $2,000, not counting the customer's downtime cost of $2,500 per hour. Our deployment covered 18 apps, digital SOP guides built on our AR platform that use real-time image comparison to verify each assembly step. The system checks whether the correct components are installed in the correct orientation, records the result, and flags deviations immediately. Trainees receive instant feedback rather than waiting for end-of-line inspection, accelerating skill acquisition dramatically. Training cycles dropped from 90 days to 30 days, a 67% reduction, and the platform is now embedded in the company's standard onboarding process. Looking ahead, the roadmap extends this capability through the NVIDIA Omniverse platform. In collaboration with NVIDIA, we are developing a vision language model-based diagnostic agent that can autonomously identify machining anomalies, chatter, tool breakage, wear, overcut from 3D mesh and point cloud data. The agent will combine sensor signals with a RAG knowledge base to pinpoint root causes and generate maintenance reports. This work, currently in legal review for a $600,000 collaboration agreement, represents the next frontier, a fully autonomous manufacturing intelligence layer built on open industrial standards. Thanks for your time, and I look forward to your feedback.
Thank you, Shuapeng. We've heard lots of truly great insights from all our speakers today. To wrap up this forum, let's welcome Dr. Bingxiang Yang back for some closing thoughts.
As today's forum concludes, I thank you for being a part of this deeply insightful and enlightening exchange. Your passion for innovation and our shared dedication to the future of manufacturing have made this session truly exceptional. Through the insights shared by our researchers, we have delved into the transformative power of intelligent mechatronics in driving the evolution of Industry 5.0. We have witnessed how these cutting-edge technologies are revolutionizing production processes, enhancing efficiency, and ultimately paving the way for a more sustainable and competitive industrial landscape. Let this forum serve as a stepping stone towards forging new partnerships and nurturing the growth of intelligent manufacturing and mobility. I encourage you to stay connected. Please feel free to reach out to us through the contact information provided below or engage with our regional offices. Once again, thank you all for your active participation, and I look forward to meeting you again in future endeavors.
Thank you, Dr. Yang. We hope today's forum has sparked some fresh inspiration for your future projects. That's all for today, but the conversation doesn't stop here. First, scan the QR code on screen or click the link below to grab your free copy of the Journal of Industrial Mechatronics. Next, leave a comment and let us know what you think. Finally, to collaborate or explore these exciting technologies, reach out to us via the contact info below. Thank you so much for watching, and see you next time.